To start, press any key. Where's the any key? I see esc, catarrh, and pigup. There doesn't seem to be any key. Computers can do that?
Triangles and polygons. Now on page 152 of your textbook, which I recommend taking out and turning to that page now, it does a really nice job of showing you what all of the possible combinations of a median of a triangle, an altitude of a triangle, and the angle bisector of a triangle could look like. So I highly recommend taking that out. I'm just going to go through a quick overview of what the definitions of these things are. An altitude, basically, of a triangle is drawn from the vertex and is perpendicular to the side across from that vertex. So it would be the line that's drawn, which is perpendicular to it. And since there are 3 vertices in a triangle, there are 3 different altitudes for a triangle. But let's say I name this. This is AX, and this is B and C. You could use definition of altitude in a proof by saying that AX is an altitude. It looks like IG, but it's is, trust me. An altitude, if and only if it is perpendicular to its opposite side. So that would be that AX is perpendicular to BC. So that's basically what the definition says. It's perpendicular to the side across from that vertex. The median of a triangle is very, very similar. In fact, I'm going to name this triangle the same thing, ABC, and I'm going to draw the median of the triangle, this point X. The median is drawn from a vertex to the opposite side, and it bisects the opposite side of that triangle. Now, be very careful because but by bisecting it's passing through the midpoint. So here's what the actual definition of the median is that AX is a median if and only if X is the midpoint of BC. Okay, so it lets you conclude that this point X on the opposite side is the midpoint. So if you know it's the midpoint, you know it's a median, and vice versa. It is a biconditional statement. Okay, moving down. Formulas for measures of angles and polygons with n sides. Well, we had gone through that whole process for deriving these formulas. So if you're curious where that came from, you can go back and look at your notes. But the sum of the interior angles, of all the interior angles of any polygon, is 180 degrees times the number of sides minus 2. Remember, this n minus 2 represented the number of triangles that could be formed inside that polygon. And since there's 180 degrees in each triangle, and this is the number of triangles, that gives me the total number of angles. The sum of the exterior angles, it turned out, was the same regardless of the shape we looked at, and it's 360 degrees, or 1 full revolution. If we're dealing with a regular polygon, that means that each angle has the same measure. So if I know the sum, and I divide by the number of sides, which is represented by this n, I'll have the measure of each one. So this is the measure of each interior angle of a regular polygon, which is an equiangular polygon. And the measure of each exterior angle would be the total sum of all the angles divided by the number of angles I have. So those are all the formulas. So to use them, here's a couple of examples. What's the sum of the interior angles of a 12-sided polygon, or a dodecagon it's called? Well, I want the sum, so I'm going to be using this formula, 180 times n minus 2. N in this case is 12, the number of sides, so this is 180 times 12 minus 2, which is 10. So the sum of all these angles would be 1,800 degrees. If I want the measure of one exterior angle of a regular 6-sided polygon, so it's regular, also I'm looking for one exterior angle. Well, all the exterior angles, the sum of them is 360, and I have 6 sides. So if I divide 360 by 6, each exterior angle will be, sorry, that should be 60 degrees. Okay, next page. In a triangle, the largest side is always opposite the largest angle, and the smallest side is always opposite the smallest angle. And if I look at a triangle, that can start to make sense. Notice in my triangle that my largest side here is across from my obtuse angle, and my smallest side here is across from the smaller of my two acute angles. That's all that's saying. In a triangle, the third side is less than the sum of the other two sides, but more than the difference of the other two sides. Remember, when we derived this theorem, we used the example of when you're walking to lunch every day. So we could draw a little quick example. Say this is here Frost Hall. Here's the exit of Frost Hall. Over here is the Dolan Center with its entrance, and we have the pathway that comes out of Frost Hall, goes over and across. Well, the sum of those two sides would be longer than if I took a shortcut across the grass here. So the sum of these two sides has to be longer than these, and this side needs to be more also than the difference of the other two sides. So putting those into practice with these examples here. In triangle ABC, the measure of angle A is 20, the measure of angle B is 60. What side is the longest? Well, let's sketch a triangle so that we have an idea of what it's talking about here. So I have one very acute angle, one angle that's roughly 60 degrees, so this triangle kind of approximates that for me. I'm going to label my angles. This is 20 degrees, this is 60 degrees, and 20 plus 60 is 80, and since the sum of all three angles in a triangle is 180, this has to be 100 degrees. So this is angle A, this is angle B, and this is triangle ABC, so this would be C. So which side is the longest? Well, the side across from the largest angle, which is side AB, would be the longest. And the smallest would be the one across from the smallest angle, which in this case is side BC is smallest. Okay. In triangle MNO, MN is 12, NO is 17. State the range of possible values for MO. Well, as we noted up here, the third side has to be less than the sum but greater than the difference. So my third side, MO, has to be less than the sum of the other two sides, which should be 12 plus 17, or 29, but greater than the difference of those two sides. 17 minus 12 would give me 5. So that is the range of possible values for MO. It could be greater than 5, but has to be less than 29 in order for this shape to actually form a triangle. Now there are three types of triangles, and it turns out that the relationships of the sides tells me what can indicate to me what kind of triangle I have. So if a squared plus b squared equals c squared, remember that this is actually the Pythagorean theorem, and that relates only for right triangles. So this would be for a right triangle. So let's see what happens in these other two situations when a squared plus b squared is less than c squared and when a squared plus b squared is greater than c squared. So here I have a right triangle. It's 90 degrees. A squared plus b squared equals this value, and also that value is c squared, so I know that it's a right triangle, Pythagorean theorem. So let's see what happens if I make this an acute angle. We'll notice that c squared is now less than a squared plus b squared, and that's true for any acute angle as I make this triangle smaller. And when I make this triangle larger, an obtuse angle, c squared becomes greater than a squared plus b squared. So the relationship we can use to determine what kind of triangle I'm dealing with is the following. When a squared plus b squared is less than c squared, it turns out that I have an obtuse triangle. When a squared plus b squared was less than c squared, that turns out I had an acute triangle. So those are the three types of triangles I can use to determine with this relationship. So let's use that in an example. If I have 5, 10, and 12, the first thing I'm going to do is identify my largest side. Now my largest side will always act as my C when I'm using this relationship to test. The 5 and the 10, it doesn't really matter. A and B, they're both legs, so it doesn't make any difference. So I'm going to do 5 squared plus 10 squared, which would give me 25 plus 100, or 125. No! And I'm going to do C squared, which would be 12 squared, which is 144. Well, since 144 is larger than 125, c squared is bigger than a squared plus b squared, so I have an obtuse triangle. Okay. The hinge theorem we will go over in class tomorrow, so be sure to remind me to ask me about this in class tomorrow.